Alright guys, today we're going to start our study of trigonometry with this first section, angle and their measures. Trigonometry is the measurement of triangles, but before we get into dealing with triangles, we're going to have to define a couple of things and make sure we're familiar with the terminology, and we'll start with angles and their measures. The first thing we're going to define is what an angle is. So pretend we have a rate here, and as you know, a rate starts at a fixed point right here, and it goes in one direction. So pretend we have this rate right here, and we're going to rotate it right in some direction. Just for sake of simplicity here, we're going to rotate it counterclockwise, and then we get that. Now we're in the plane here. We're going to label a few things in here, and we have this point here where those two rays intersect is what we call the vertex. Okay, this first initial side ray is called the initial side, and this would be the terminal side. Okay, so the rotation of this rate is going to form an angle there, and that's how we're going to define an angle. So an angle is determined by the rotation of the ray about its endpoint. A couple of things here. So we have an angle that is formed by the rotation of that ray, right? Because I'm in space or in the plane, we can move this anywhere we want. We're gonna have to have some sort of a standard position here to just keep track of the angles. So we're going to define what a standard position is. So I'm going to go ahead and place this initial side right here on the positive x-axis, and then of course the terminal side would be wherever that lands. So let's say it lands on the second quadrant there. We have our angle here, so let's call this angle theta. So this is a standard position. Standard position means you're going to place all of the angles in standard position are going to start on the positive x-axis, and then they're going to go around either clockwise or counterclockwise to their terminal side, right? And so that opening forms that angle of interest here. Now, some notation here for angles are the letters. Typically, the letters that we're going to use, the symbols that we use for angles. So we're going to use alpha, beta, gamma, theta, and so forth. Now, I have mentioned about going clockwise or counterclockwise, but that would be a good time to mention positive and negative angles. So from now on, we're going to just basically every time we graph or we're picturing an angle, we're going to think of it as in a standard position. So always start on the positive x-axis and then go from there, go to the terminal side. So we're going to, every time you have an angle that goes from the initial side to the terminal side in counterclockwise direction, then that angle is going to be positive. And if you go clockwise, like this way, I'll call this alpha. Alpha will be negative. So that's alpha less than 0. This theta is greater than 0. So in other words, this is positive and this is negative. Okay. So notice here again, positive means counterclockwise, negative, or clockwise means negative. So that's very important. Now would be a good time to also define what coterminal angles are. So coterminal angles, just kind of like what the word says here, they're going to be angles that, remember, from now on we said we're going to use standard position. So all angles are going to be starting from the positive x-axis in standard position, and they'll go to the terminal side. So, we're going to assume they're all going to be in standard position. So coterminal just means both of them also have the same terminal side. These two angles here, theta and alpha, would be coterminal. Even though one is positive and one is negative, notice how the definition just say they both have to have the same terminal side. They're both starting from the initial side, the same initial side, and then one goes counterclockwise, the other one goes clockwise. which makes one positive and the other one negative, but they're still coterminal because they both have the same terminal side. So we're going to see some examples here. Okay, well, before we start actually finding, doing some concrete examples with actual numbers, let's go ahead and define the first measure for angles. The degree measure just comes from something that we either used in the past. I mean, we just know to be a fact because we've been using it over years and years and centuries after century, and that's the fact that one revolution here is 360 degrees, right? So most people already just know this intuitively or because they just know it or heard it from somebody. So, but basically the definition of 1 degree is going to come from the fact that the whole revolution is 360 degrees. So 1 degree is going to be equal to 1/36th of a revolution. So notice how the definition comes from the fact that the whole revolution is 360, right? Again, you may ask yourself, where did that 360 come from? Who came up with that? So we're not going to get into all that, history, but basically it could have been just anything else. It could have been 400, it could have been 500 for all we know. But again, 360 just happens to be a very convenient number because it's divisible by a bunch of numbers. So, but we'll leave it at that. 1 degree, we're going to say, is 1/36th of a revolution. You can see right away, if 360 is the whole revolution, half a revolution would be 180. Quarter of a revolution, which is what we call perpendicular, that would be 90 degrees and so forth, right? And you can see how you can split them, and that's the convenient part of the 360 number, that you can divide it evenly into whole numbers. Recall this is the first quadrant. We always start there and we go counterclockwise. Second quadrant, third quadrant, and fourth quadrant. Now in terms of degrees, you can see how this is 0 degrees, but it's also 360 degrees, because you go around. This is the 90 degrees, 180, and this is the 270 degrees. And then again, we go back to the 360 degrees. So keep this in mind, because, we'll use, quadrant 1, quadrant 2, make sure you know which quadrant is which. Now, knowing what, the degrees are, we can now try to do some examples with coterminals. How do we find some coterminal angles here? Now, notice here, let's go back to what we defined here, coterminal angles. Now, notice here, if you can see the pattern of how to find a coterminal angle. So let's say this alpha, right? This alpha is, let's say, 210 degrees. What would this beta be, right? And again, we just discussed that the whole revolution is 360. So if this whole thing is 210, then the beta will have to be 150, right? Now, remember what we said about positive and negative. Because beta is going clockwise, then it will have to be negative 150. And always make sure when we're dealing with degrees, because we're going to see a different type of measure, that you always put your little circle there so we know we're talking about degrees. All right, well, see here on this example. Let's say this alpha is 60 degrees. Okay, what would beta be? And again, notice how beta went around one time, a whole revolution, which we know is 360, and then it goes the same distance or the same opening that 60 degrees that the alpha is doing. So it'll be the 360, right? The 360 there, plus that 60 from the alpha, that will give you a 420. You can quickly realize that because we can go around as many times as we want, or in either direction, clockwise or counterclockwise, we can come up with an infinite amount of coterminal angles, right? So there's a pattern here, right? And the pattern is the following: theta plus 360 degrees n where n is just an integer. Now this should make sense, right, guys? Because look at what we did over here. To find a coterm, or to find beta, we added 360 to this 60, right? And we got the 420. Okay, well, if you say, well, how do we find the negative? Well, we can also subtract. So to this beta, to this alpha, 210, if we wanted to find a coterminal angle to 210 going the other direction, or a negative one, you would subtract 360 from 210, and that's how you get the 150. Now remember, you can do that as many times as you want. You can go around, and that's still an angle, so that's why it's n, because this n could be any integer, right? It could be all the positive 1, 2, 3, 4, and that will go around as that amount of times, and also it could be -1, -2, so that will go the other way, the counterclockwise. Here's an example. Let's say this is theta. Theta is 30. So then this angle has to be 390, right? Okay, in the same way, if we have same theta equal to 30, the clockwise angle here going the other way would be 30 minus 360, so that will give you the -330. So all of these are coterminal angles to 30 degrees. And ultimately, again, you can come up with an infinite amount of coterminal angles. I mean, you could have your theta in there. You could just keep adding 360, keep adding or subtracting 360 degrees, right? So those are coterminal angles. So some things that will come in handy later on as we move forward here in these sections of this chapter here. Now a couple more things I want to mention before I go to the other measure is maybe some things that you've seen in geometry if you're taking a geometry class, but if not, they'll be worth just mentioning them here. All right, so the first one is complementary angles, and that's when you have two angles that add up to 90 degrees. And then you have also supplementary. So you have two angles that add up to 180 degrees. Simple as that. So now, of course, this only makes sense when you have positive angles, right? It's just not only going to make sense when you have positive angles. So like, for instance, the example of the 30 here, two complementary angles would be the 30 degrees and the 60, right? Because the sum of the two is 90 degrees. For the supplementars would be 30 and 150, because the sum of the two is 180. So again, don't mix this up. Complementary angles are two angles that add up to 90 degrees. Supplementary are two angles that add up to 180 degrees. We are now ready to define what the second measure here, and that is the radian measure. Okay, so this is the one that we're going to kind of work towards, and eventually in calculus, we use radians all the time. So you want to start getting used to transition from thinking in degrees to thinking in radians. And the way that radian is going to be defined, this one does have a mathematical explanation here. It's going to be, well, let's draw our little XY plane, and then let's position an angle here. We're going to call the length of this ray, let's just for the sake of it, we're going to call it R. So this would also be R because that's the same ray. And this length S, let's call this arc length S. We are going to let that, so we're going to open this, make this angle so that the arc length here is actually equal to R, to this R. Now notice how this does not depend on what R is. As long as you make this R length the same as the length of the ray, then this is going to work. So when you have that setting right there, the angle that is in here is 1 radian. Okay, so that is the definition of a radian here. If we had to guess here, right, what, how many radians we need to do a whole revolution. So remember how in degrees a whole revolution is 360 degrees. Like, we know roughly what a radian is here. How many radians would you need to go around a whole revolution? It turns out it's a little bit more than 6, but we actually have a way to find them exactly how much it is. So we're going to recall our the circumference of a circle. Now remember, if this keeps going around, you're going to get the circle here. If you recall, I'm going to just put it over here. The circumference of a circle, 2 pi r, where r is the radius of the circle here. And if, just for the sake of simplicity, remember this does not depend on how big or small the circle is, or how big r, how long r is. If we make this r longer, right, the whole circle will be bigger, but the opening, the angle will still be the same. So why don't we just let r be 1? So if you let r be 1, this s would also be 1. And since we know this is a radian, this r length would actually, the quantity of the r length would actually match the radians here. So it would be very convenient. So if you let r be 1, okay, then we plug that in here. The circumference is 2 pi times 1, which is just 2 pi. This is 2 pi. This will be the r length if this circle has a radius 1. But remember, we said the r length, the circumference, is going to match the actual angle in here, the actual central angle. So then we conclude that 2 pi, 1 revolution is equal to 2 pi. Now remember how we said it was about 6, a little bit more than 6? Well, you know pi, this number is, 3.14 ... which is 6.28 ... So notice how it is, in fact, a little bit more than 6. Of course, this is an irrational, pi is an irrational number, so we're not going to be able to exactly approximate it, but we're just going to leave it in terms of pi. So rule of thumb here is going to be, if you have pi there, to just leave it in terms of pi, unless your instructions say otherwise, or you're actually working through a word problem, you have to round, come up with an approximated amount. All right, well, there you have it. And now that we have the two measures, radians and degrees, we need to have some sort of conversion here. Okay, so how do we have a conversion here from degrees to radians and vice versa? So we have degrees, radians. It's very straightforward here, guys. So to go from degrees to radians, you're just going to multiply by pi over 180 degrees. And guess what you're going to do to go backwards is just you're going to flip that 180 degrees, multiply by 180 degrees over pi. Okay, so very straightforward here. Now remember, guys, this is should make sense, the factor here, because remember, a revolution here is 2 pi, so that means half of a revolution is pi. So pi, and in degrees we know half a revolution is 180 degrees, so really this is pi over 180 over pi. That's like you're multiplying by 1, so all you're doing is just changing the units here of the measure. Notice how going from degrees to radians, you want to have that radians on top here, so that's what you end up with at the end. Same thing here, from radians to degrees, you want to end up with degrees, so the degrees got to be on top. The radians cancel out there, and we'll see a couple of examples here, but that's basically all you have to do. Now eventually we want to start thinking about in radians, but you have this conversion factor to be able to go back and forth between the two. Something else here on the degree part, let me go ahead and just, now that we know radians, we can, this coterminal definition here, I can convert that to this. Remember how we said we can add a multiple of 360 degrees to an angle to find a coterminal angle? Well, in radians would be 2 pi. And again, it's the same thing, and it's an integer. All right, also for complementary and supplementary angles, this is, okay, we have now alpha and beta. If they're in radians, 90 degrees is pi halves. If supplementaries would be alpha plus beta would be equal to pi is 180 degrees. So I'm just converting everything to radians here. So everything is going to carry over the same, it's just we're in a different measure. Right. And then we have our conversion here to go back and forth. Right, so let's look at an example here. Okay, so convert pi 6 into degrees. We're going from radians. Now, something else I forgot to mention here, guys, that remember I said for degrees, always put that, make sure you put that little circle in there so we know that we're doing degrees. For radians, you don't have to write the word radian. If you just leave it without units, that's understood that we're talking about radians. So for radians, you can just use the quantity, and if it doesn't have the little circle or anything else, we're going to assume that's radians. So here pi 6 is just a number, real number, so then that's understood to be radians, and it's also telling you to convert it to degrees. So we're going to use our conversion factor going from here to here, multiplied by 180 degrees over pi. So we take pi 6 times 180 degrees over pi. And notice how this is going to work out nicely, because you know the pi's go away and you have 180 over 6, which simplifies nicely into a 30 degrees. Also vice versa, if you're asked to convert degrees to radians, say for instance convert 135 degrees, notice how I have that little circle there into radians. Make sure you don't forget your units here and your right notation here. So we're just going to multiply 135 times, and now we're going to use the other factor here, which is pi over 180 degrees. And yeah, guys, when you're doing degrees to radians, sometimes it may explicitly tell you this or not, but like always assume, always leave your answer in terms of pi. Okay, so don't compute unless again you hear otherwise or the instructions say otherwise. Always leave this in terms of pi, meaning I'm not going to compute pi in the calculator because that's going to give me an approximation. So I'll just simplify this as much as I can. 45 actually happens to go into 135 3 times and goes into 180 4 times. So this comes out to be 3 pi over 4 radians, and we don't have to write the word radians there. All right, guys, so I mean the same way you can find, you know, like if we go back to the examples that we have a complementary and supplementary angles, you know, in degrees you have to add up, they both have to add up to 90 degrees, but in radians they have to be pi. But you know, if you convert these things to radians, and eventually you'll know this right away, but this 30 degrees is actually pi over 6. We did that one down there, and this is pi thirds. If you add these two fractions, it will give you the pi halves. I think it's a little bit easier to see on the supplementary. So here this is pi 6 for 30, and this is 5 pi 6 for the 150. Notice how you're really adding just fractions. These are fractions in pi, so this is 1/6 plus 5/6 gives you 6/6, which is 1 pi, right? So if you're good around fractions, then you should be able to quickly do those. If not, you can always use your conversion to go back and forth. It may take you a little bit at first, but hopefully eventually you would, you know, with practice, get a little bit more proficient with using radians. Now that we know both measures, and there's going to be a bunch of applications that or formulas that are used using this radian measure. So again, I'm not going to mention all of the ones that are there, but some common formulas that I kind of mentioned here earlier too is the arc length formula, area of a sector. So okay, so there are some with linear and angular speed, but the most common ones are the finding the arc length and the area of a sector. So we have, if I'm labeling this S or this arc length to be S, there's a nice formula here. S is equal to pi r, or r pi, whichever way. The area of a sector, we have that 1/2 r squared theta. Okay, so the important thing about these formulas is that you want to make sure if you're going to use these formulas, these thetas have to be in radians. That's important. I mean, you can derive equations or formulas for this same arc length and area in terms of degrees, but there will be a little bit more involved. You have to do the conversion. So just make sure if you're going to use this formulas, always use the angle in radians. And if it's not in radians, then you can use your conversion factor here to get in radians before you plug them into these formulas.